In this video, we'll be going over percent ionization. So this is related to our weak acid pH problem solving and equilibrium. Okay, so let's get started. So first of all, definition. So percent ionization is, if we come up with our concept of percentages, it's a portion out of a total. So percent ionization means the percent that actually the percent of the initial amount that went over to the product side to become ion. So that's the ionized side is the product side. So it's the portion of the initial amount, the fraction of the initial amount that went over to the ion side. So it's exactly what it says it is, percent ionization. So another way to say it is they're actually giving you X on the C line of the ice table. So they actually, so we can actually write a little formula for percent ionization. So I have those out of order. Okay, so we could write a little formula is percent ionized equals X over the initial amount. Okay, so HA is just generic acid. Okay, the initial amount. So that 0, remember, means initial. Okay, so and this X right here is how much stuff became ions. How much stuff turned into ions, became ions. Okay, so this problem here, it says calculate the percent ionization in a 1 molar solution of nitrous acid. And in example 2, it says calculate percent ionization in a 0.2 molar. So it got diluted in number 2. We'll take a look and compare the results real quick. Okay, so here's the problem. So I'll write out, so nitrous acid is HNO2, H plus NO2 minus. So I'll make my ice table, and the initial amount is 1.0. These are zeros, okay, and the this is going to be go down by X. This goes up by X. This goes up by X. Okay. Now, if I solve for X, that's going to give me how much became ions, so how much went over to be ions. And the percent ionized is all I need to do is, for the percent ionized, I just need to figure out what X is. So how much of this went over here? Okay, so I need to figure out what X is, and then divide by the initial amount. And that will give me the fraction that went over there. And then I just times it by 100 to get the percentage that became ionized. Okay, so if I now this is actually getting, this is actually kind of strong, 4.5 to the negative fourth. But I'm going to trust that that's big enough to where X won't put such a big dent in that number. So I'm going to use the assumption rule, 4.5 times 10 to the negative fourth. And if you, to the keen observer, this is actually a check of the assumption rule. So if we get percent ionized, if it's greater than 5%, then I need to go back and do this problem using the graphing method or quadratic formula. So this is going to be X squared over 1.0 minus X, and I'm going to assume that this is negligible compared to the 1.0. Okay, and so my X will be the square root 4.5 times 10 to the negative fourth. So for this I get 2.1 times 10 to the negative second molar. Okay, and so what I just figured out was this number. So I want to get the percent that went over there. So what fraction of the whole is this 2.1 to the negative 2? So my whole was what I started was 1.0. Okay, so for percent ionization, I go X over the initial, which is 1.0, okay, and then times it by 100. Okay, and for this I get 2.1% ionized. Okay, and so notice this is less than 5%, so my assumption rule actually works here. So the assumption rule works. Okay, so let's try it when it gets a little more dilute. So I run it through the ice table, and then I wind up with this. I'm just going to change this number right here because that's essentially what's happening. Is the equals x squared over 0.20. Now it's pretty risky to use the assumption rule, but I'm going to do it anyway. So minus x. So this is again, so I'm going to assume, because I'm basically, you know, when I run through this problem, I'm checking this anyway. I'm checking to see how much of the initial is x, is what percent ionization is actually. So if I solve this problem here, I get x is the square root of 4.5 times 10 to the negative second times 0.20. Okay, so for this, I get 9.5 times 10 to the negative third molar. Okay, and for percent ionization, I'm gonna take that x and go over 0.20 times 100. So for this, I get 4.7%, which is really close to 5%. So and if I just to show you what that means, if I take the 0.20 and I subtract here, so I'll take the 0.20 minus the 9.5 to the negative third, I get so minus x, I get 0.19 0.19 molar. Okay, so if I graphed it, I'm gonna get really close to really close to this anyway. Okay, so this is a 4.7% ionized. There's a little generalization I can make. I'm out of space on the bottom. So if you noticed that this was diluted here, and it was 1, and so notice the percent ionized. So the more dilute, the more it actually needs to go make ions, and this agrees with Le Chatelier's principle. So if I have my beaker and I have a whole bunch of solvent, it needs to the equilibrium is going to shift more to the right to try to make more ions, to try to occupy that huge amount of solvent that you have. So this agrees with Le Chatelier's principle also. So the more dilute, the more percent ionized it actually will become. So I'm going to generalize that and say the more dilute your sample, the more percent ionized it'll be. That's a conclusion we can make from doing this problem. Okay, so here's a slightly different problem. Is now I have, this is asking me to calculate Ka. Okay, when they give me the percent ionized, realize that they're giving you X on the C line. So, and if they gave us the initial and they gave us X, then we're going to know the equilibrium amounts and we could find Ka. Okay, so let's go ahead and set this problem up. Okay, so the amount ionized is X again. So if they give us, so let me write out our ice table here. So they gave us, this number is 0.15, which is this number here. That's the initial amount. 0, 0. So they're giving us X by telling us the percent ionization. Okay, so because we need these to get Ka. So Ka is going to be H plus at equilibrium times A minus at equilibrium over HA at equilibrium. So I just need to figure out what this is, and I'm going to use that formula I had before. So this is X over 0.15 equals, and they gave us the percent ionization. So I'm going to turn that into a fraction. So I'm going to go 0.030. Okay, and if I solve for X, this little side work is going to give me these numbers here, which will allow me to calculate Ka. So this side work, I get 0.0045 molar. Okay, so this is going to be 0.15 minus 0.0045, and this is 0.0045, 0.0045. Okay, so now I'm going to go ahead and put this in for this number here, and this number here, basically square that. Okay, so Ka is going to be 0.0045 squared over 0.15 minus 0.0045. So for this Ka, I get 1.4 times 10 to the negative fourth. Okay, and I have a your turn on the next slide. So this is for you guys to try. It should be pretty similar to, notice this is pretty heavily ionized. Okay, so you should get a high value for your Ka, I think, on this one. Okay, so that's the end of our video.